The next application of integration that we're going to look at in this series is the average value of a function. So that is when we're given a function like the one shown over here, and we want to find the average y value of that function, or sort of the average height over an interval. So for this, we're going from -3 to +3. And the idea is we'd actually find sort of the area of that function and then average it out as a rectangle. So we want to ask ourselves, if we took the area under that curve, and if it does go below the x-axis, the important thing to note here is we actually want to keep that signed area. So if we take the signed area under a curve and we spread it out between the start and end point, so we create a rectangle, what is the height of that rectangle? What's the average value of that function is the question. So the rule that we have for the average value is we do 1 divided by b subtract a, so that's sort of dividing by the width of the interval, for the signed area from a to b of f of x dx as an integral. So for this particular example, we're going to have that the average value is equal to, and we're going to go from -3 to +3, so that gives an interval width of 6. So using this formula, we'd have 1 divided by, and b subtract a would be 3 subtract -3. And then we'd have the integral from -3 to +3 of the function f of x, which is 9 minus x squared dx. So this is going to equal, and if we just take a look at our graph for a moment, we can see that the area or the region of the curve that we're interested in is actually symmetric about the y-axis. So that means we could just calculate half that area and double it. So I'm going to use a 2 here, which is going to double the integral's value, divided by 3 subtract -3, which is 6, or the length of the interval. So I'm going to have 2 over 6 times the integral, and instead of going from -3 to 3, I'm going to go from 0 to 3, and again doubling that value using that property of symmetry that we have for this particular question is just going to simplify some calculations later down the track. And of course we still have 9 minus x squared dx. So this is going to equal 2 over 6 is 1 over 3 times the antiderivative, which will be 9x minus x cubed over 3, and that's adding 1 to the power and dividing by the new power. And we're going to evaluate that between 0 and 3. So that's going to equal 1 on 3 times, and then we'd substitute in the upper value into the antiderivative. So we're going to have f of 3 subtract f of 0, the lowest value substituted in. So this is going to equal, and the trick here is not to leave anything off. So we're going to have this third multiplying, and then first of all we're going to substitute 3 into this antiderivative. So we're going to have a couple of brackets here. We're going to have 9 times 3 subtract, and it's going to be 3 cubed over 3. And then we're going to subtract away the lower terminal of 0 substituted in here, but all of that's just equal to 0. So that simplifies things for us. That's the benefit of noting that this was symmetric about the origin. And this is just going to give us 1/3 times, and then in that first bracket we're just going to have 9 times 3 is 27, and then we're going to have minus 27 over 3, which is minus 9. So all up we have 1/3 times, this is 18, which equals 6. So 6 is the average value. So where we had this question mark here, if we get rid of that, this is just going to give us y equals 6, is the average value or the average height of that function between -3 and 3. So I hope that this video has helped you gain a better understanding or a good introduction to the average value of a function. Make sure you stick around for the next part of the series that's coming, and that will cover the application of integration or anti-differentiation to kinematics or straight line motion. So make sure you stick around for that. Check out in the description below a link to the other videos that are a part of this series. And once again, I hope this has helped you learn something about integration.